Hello everyone. So today we're going to talk about the formation of igneous rocks. Up to this point we've talked about the three types of rocks kind of briefly. Now we're going to get into a little bit more detail about igneous rocks and how they form. We've already said this in class, that when igneous rocks form, they can form by making very small crystals. Those are aphanitic rocks. Rocks where there are large crystals would be called phaneritic rocks. Rocks that have cooled so fast that no crystals have formed at all are called glassy. That would be like an obsidian rock. Or vesicular, which is kind of like pumice, where you literally get like a lava cooling so fast that gas bubbles are trapped as that material is cooling in this glassy form. So basically we've got these four types of textures for igneous rocks. And this leads us to a couple of terms that we have not used in class yet. Intrusive. Intrusive means magma within the earth, deep within the earth, has cooled very slowly. And that would result in very large crystals being formed. Those would be phaneritic rocks. And extrusive, where magma has come to the surface and now it's called lava. And lava at the surface cools very quickly and it forms very small crystals, or possibly even a glassy material where crystals have not even had a chance to form. So again, large crystals take time to form and small crystals happen very quickly, okay? All right, so this is going to lead us to the new stuff that we're going to talk about. It was realized about 100 years ago, more than 100 years ago, that if you took one single huge mass of magma, which presumably is all made of the same stuff, you could take this one mass of magma and form many different types of igneous rocks. And there was a scientist, a geologist, that figured out how this could possibly happen. His name was Bowen. We're just going to use his last name. Frankly, I've forgotten his first name. But anyway, we're going to be investigating Bowen's reaction series. Bowen's reaction series, it's going to seem kind of complicated, but before we even get into it, I want to emphasize how when you're working with Bowen's reaction series, you're always going to have a reference table to work with. Okay, you'll see what I mean in a minute. Okay, so we're going to start with this slide, and what this slide is showing us is that there is a mass of magma deep within the earth, okay? This mass of magma, because it's deep within the earth, would be recognized as intrusive. These crystals would grow very slowly with time. And as we're talking through this, we'll see what's going to happen. Before we get into Bowen's reaction series, though, let's just make a quick generalization. Igneous rocks can be categorized by their silica content. Basaltic rocks have low silica content, while granitic rocks have high silica content. And really, up to this point in geology, we've seen basically two types of Earth's crust. We saw oceanic crust, which is really basaltic rock, and granitic rock, or rock that is relatively high in granite type rocks, would be like continental crust. Okay? Okay, so here's Bowen's reaction series, and I'm sure that at this moment, right now, you're looking at this and you're thinking, oh my God. Okay, so let's, just take a look at this together and walk through this. It's really not as daunting as it might look. Okay, so let's just take this in steps. Okay, so let's just start with looking at this graph or this table and seeing what it's telling us. All right, so just bear with me here. So looking at the left side of this table, we've got temperature. All right, and looking at this table as we go down, we see cooling going on. So we're going from highest temperature to lowest temperature. When we're thinking through the Bowen's reaction series, let's just imagine one huge mass of magma. And let's just start with this massive magma at, let's say, about 1500 degrees Celsius. Okay? So 1500 degrees Celsius, everything is melted. Okay, well, let's imagine that part of this magma mass begins to cool. And let's say it cools to a point where it's 1400 degrees Celsius. What is going to crystallize out first? We've got this massive magma. What are the first crystals that are going to form? Well, the first crystals that are going to form out of this magma would be olivine. Okay? And what else might be crystallizing out? Oh, calcium-rich feldspar. Okay? And again, you're not memorizing any of this. We're just reading the table. Okay? Or reading the graph, or I'm going to call it a table. Okay. So this massive magma just began to cool. We're at about 1400 degrees Celsius. What has crystallized out? Olivine and calcium-rich feldspar. Okay? All right, let's take this mass and continue to cool it. It continues to cool. Now what begins to crystallize out? Oh, we're way below, let's say, 1400 degrees Celsius. Pyroxene begins to crystallize out now. And we still have some calcium-rich feldspar. But as we go down this side of the series, okay, as we get to cooler and cooler magma, we're going to develop more and more sodium-rich feldspar rather than calcium-rich. We start with calcium-rich, that crystallizes out first, and over time we get more sodium-rich feldspar coming out. Basically, the way that this would look, calcium-rich feldspar is very dark, and if you think of basalt rock is very black, right? I mean, we've seen this in the lab. Basalt is very black, but as you become more and more sodium rich, it becomes lighter in color. Okay, we're continuing to cool down this lava or magma. The magma is cooling farther. We begin to form amphibole out of this magma. We cool it down further. We begin to get a lot of biotite mica coming out. Okay? Now, if there's enough silica in this magma, all right, if there's some silica left over, we will continue to crystallize out as we go into lower temperatures. We'll get potassium feldspar coming out or muscovite mica coming out. And if there's even still some silica left over, we might even get some pure silica crystals called quartz coming out. Really, this all kind of depends on the amount of silica that is in this magma. If there's not very much silica in the magma, we're going to stop forming crystals when we make basalt or gabbro. Okay? If there's a lot of silica in this magma, it'll go on and on and on and crystallize finally out to a bunch of granite, really. If you've ever looked at granite, if you remember what granite looks like from the lab, when we were in the lab, you would tend to see a lot of pink minerals. That's potassium feldspar. You get a lot of shiny crystals. That might be the muscovite mica. You also see a lot of clear crystals or white crystals. That would be quartz. Okay? So again, the more silica, the more granite you're going to form. The less silica, the more basaltic the rock is going to be. If you've got little silica, you stop with basaltic rock. If you got a lot of silica, you make granitic rock.